All right, welcome to the introduction to the integrity management for hazardous liquid pipelines, and that's found in 49 CFR 195.452 is the section that covers it. This is the Module 1, the overview and spill models section. We're going to cover a variety of modules. We're going to look at the life cycle here in a minute, but there's going to be 5 modules, and each module will tackle different portions of the integrity management life cycle. Before we get started, I do like to give a shout out to the Code of Federal Regulations, the eCFR, if you will, is put out there by PHMSA. It's a great resource. They keep it current, so if you need to know what the latest in the code is, you can go there. There's the website on the screen there, but they keep it current, and I would encourage you to sign up for email alerts for the different parts of the code that are important to you. You can sign up, and if that part changes, they'll send you an email that says it has changed, so you're always aware when the code has changed. So I encourage you to take advantage of that service by the federal government. So when we think about integrity management, I call it a life cycle, if you will, but it kind of starts up at the top with the green arrows. It all starts with data integration, and then from there, based on our data, we roll into spill modeling and risk analysis. Then based on that information and the threats and different things that we discover on that, we roll into assessments. Then we keep going down. After we do the assessments, they result in perhaps some defect that they indicate. You guys possibly have some defects here or there. So we're going to evaluate those defects, make any repairs that are necessary. Then we're going to get into the preventive and mitigative measures so that we can avoid those things from occurring again. And then we're going to evaluate our program for continual improvement and see what we're doing well, what we're not, what we need to improve on, and basically we're continuing that cycle. And what we'll find is we could be in multiple parts of this cycle at any one time, and frankly, you probably will be. You may be in all of them at the same time. You're you're doing your data integration, your risk models at the same time you're doing maybe running some tools and doing some digs, making some repairs. So it's all continuous, but really the data is the key that makes it work. So one of the first things you need to do is you need to identify could affect segments, and that's we're going to look at kind of what makes up that. So it starts off with high consequence areas, and the liquids world, high consequence areas are highly populated areas, other populated areas, commercially navigable waterways, unusually sensitive areas, which are called USAs, if you will. There's ecologically based USAs, and then there's drinking water based USAs. And the federal government does provide these locations to operators through NPMS and some other resources. You have to ask for the information. They will give it to you in a file that you can download into your GIS system. But you do have to periodically update it to make sure there's no changes. And also they expect you to be looking out along your system to see if there's any other high consequence areas that maybe the federal government hasn't identified that you can identify along your right of way. So it's not all up to them, but they do provide the bulk of the information to you. So when we think about liquid pipelines, we're asking ourselves, could I affect this HCA? And it's called a could affect segment. Could this pipe segment affect an HCA if it were to fail? So in order to do that, you need to think about where would the product go? Typically, we're talking about liquid products, although there's also highly volatile liquids. We're going to talk about them in a minute. But how far could it travel over land? And that's how viscous is it? What's the terrain like? What's the elevation? Then think hydrology. Maybe it travels down through a little bit of land and gets into a creek or a river or a stream. Where does it go from there? Perhaps it traverses a creek or something, and if it was to fail right there, it would drain right into the creek. And how far would it go before you could contain it and stop it? So all that is contained in spill modeling. And then for the highly volatile liquids, the HVLs, it's a vapor cloud. If it was to break, that liquid would almost instantly become vaporized, and now you have a vapor cloud. And where's that going to go? Is it lighter than air, heavier than air? What are the winds like? And so you have to analyze that vapor cloud dispersion and how far will it go before it becomes so diluted that it's really not a harmful issue anymore. So when we think about the integrity management, we're kind of looking at it from two sides. One is, where are the HCAs? Where do I traverse an HCA, directly affect the HCA, and where could affect the HCA, where it could a pipeline could fail here and travel to and then affect an HCA. So it's a little different than the gas rule. So keep that in mind. So we use our spill model and our vapor dispersion models to help determine those could affect segments. And normally it considers things like pipe diameter, flow rate, pressure, valve spacing, terrain, elevation changes, things like that. Response times, how long does it take you to recognize you have a leak? How long does it take you to shut down the system? Then how long does it take you to get out and contain it, get the booms out on the rivers, things like that, so that you can stop the flow and the travel of these products. So keep that in mind. What is the product type, the viscosity? Is it an HPL? Is it going to vaporize, or is it going to sink to the bottom of the water? Is it going to float on top of the water? Things like that. So all that goes into a good spill model, and vapor model needs to account for all these different variables. So here's an example provided by Dynamic Risk Overland Spill Model. And you can see there the kind of the gray areas are where a liquid would escape and affect the ground, the terrain. It's going to get out on the ground and it's going to travel on the ground, but not affect a waterway. But all that light blue area is where the spill model is predicting that if a break were to occur in any one of those areas, it's actually going to travel downhill, get into that river, and then you can see that creek, whatever it is, it's going to follow that river once it gets into it. So how fast is that river moving? How many miles per hour is it moving downstream? It's going to carry all those products. And then what's downstream? Is it does it end in a river, a lake, whatever, a drinking reservoir, any of that kind of stuff? So how does it get into the water, and then how far does it travel down to the water before you can get a boom across that and contain those products? So all that needs to be included, but that's kind of how a spill model the results would look. One of the things the PHMSA wants you to know, what you should want to know, is the drain down quantities. How much, if you were to have a failure and you shut everything in, how much would it drain down? How much product would lose at that particular spot? And you can see in this particular graph, it has a lot to do with elevation and time to respond to it. But in the very bottom, in the darkest purple, bluish, darkest blue, there is takes you a while to detect it. So all the pumps are running and you're basically putting product out through some sort of hole in your pipeline, some sort of failure in your pipeline. And then it takes you a little while to shut the pumps down. So that's a little bit of a time, and the pumps are running. Now you got to shut it down. And now after that, it's a question of elevation and things, but you've got how long till you close your valves? Are they automatic valves? Do you have to go close them? And then what's the elevation profiles? Because once you close all the valves, what's upstream, uphill of that defect up to the valve, that's all still going to all drain down by gravity. So there's really nothing you can do about it at that point. Even though you got all the valves closed, gravity and elevation is going to take effect, and that is an additional volume. So a good drain down outflow analysis will stack all those up so you can see where's my maximum potential for how many barrels could be spilled from this particular pipeline. Where's that going to occur? What are those volumes? So you need to perform this analysis as well. So you see liquid, we talk about liquid spill modeling, vapor modeling is very much, is pretty complicated, and it usually you have to get some sort of outside vendor to help you with this through their software. Well, when we think about Part 195 and Part 192, sometimes PHMSA uses the same terms, but they mean something different. In this particular case, in the liquid rule 195, when they talk about an HCA, high consequence area, that's really more synonymous in the gas code with an identified site. When they think about could affect segment, where you could affect an HCA, that actually is more like what they call a high consequence area in the gas rule, where a pipeline failure there could affect a identified site. So you can see could affect segment is really more synonymous with an HCA in the gas code. So those two terms, HCA is not the same, used the same in the gas and the liquid code. So just be aware of that. So as we move through modules 2 through 5, we're going to take a deeper dive into each one of those stages of the life cycle. So we've kind of looked at the first stage, but we're going to keep moving on around that circle.